All right. Hello, everybody, and welcome back. So we're going to get started with the meat of the course now. We're going to start with the first lesson, which is, as the last video described, one of the very first things that we're going to learn how to do in this class has to do with this concept of integration, but in 3D. And in order to start there, it's super important that we first start and make sure that we really understand integration in 2D. So I kind of want to start this video by, just kind of a reminder of what Calc 2 covered once upon a time. Okay, and the idea was that let's say we have some function. Okay, so we can make a kind of a nice drawing here. And let's say that we have some function that represents whatever you want. Okay, we have some function. This is a 2D function. 2D function. Since we have x, since x goes in, y goes out. Easy peasy. And we said, let's pretend that this function is something that we eventually want to calculate the total value of. So some examples from Calc 1 and Calc 2 of what f of x could be was like it could represent the velocity of an object. Maybe it represents the probability density function, right? The probability of something happening. Maybe it represents the mass, or excuse me, not the mass, the density of an object, because you add that up and you get the total mass and center of mass and all that stuff. It could represent pretty much anything that we want. It could represent heat, right? Heat distribution. It could represent a whole bunch of stuff. And we said, if we happened to want to figure out how to calculate the total amount of something that we have, so whether it's velocity, probability, density, heat, and whether we want to do it over time or over money or whatever our x variable is, maybe we should label our x-axis here, we could do it. And the way that we started off Calculus 2 was not by jumping straight into integration, although that is, of course, where we are heading. But the idea was that we started off with these things called Riemann sums. We said, hey, if I want to add and figure out the total area under this curve, if my goal is to essentially get all of this, okay, if this is that's my goal right there. And that would give me the total of whatever it is that I'm trying to do my math on. We started off with this idea of a Riemann sum. We said, okay, well, we didn't have any tools, and we said, well, what if we just take an endpoint here and we approximate the area by just saying, that the area of this rectangle is kind of, it approximates the area under the curve. Okay, now obviously this is not entirely accurate, because if I ask you to figure out what the area of this rectangle is, you would say, okay, well, the height of the rectangle, well, that's just going to be whatever the y value is, right, at that point, right? So the area would be equal to the height times the width, and the height in our case would be the y value, which would be f of x, or in our case, it's f of a. And then what would the width be? Well, the width would just be the entire distance right here if we're just doing one rectangle, right? So for us, that would just be, we'd multiply this result by that distance, and distance is final minus initial. And so this right here, whatever this random calculation would be, this would give us, our approximation. Okay, our approximation. And, you know, we saw that if we had just one rectangle, this wasn't that good of an approximation. And we made this guess better by doing what? Well, we said that, well, how about instead of just one rectangle, what if we cut this up into not just one rectangle, but maybe we did like 2 or 4 or 5 or 10 or 100, right? And the idea was that the more slices that I put into here, and if we were doing a left Riemann sum, we would grab the left endpoint here. Maybe I'll use a different color. We'll use the left endpoint to create our rectangles, right, like so. If we were using the right Riemann sum method, we would grab the right endpoints to create our rectangles. So something like this, right? This is how you create it for using the right Riemann sum method, so on and so forth. If we were using the midpoint method, we would pick the value that's right in between our intervals to create our rectangles, right? And we could do this for all of them, and so on and so forth. There's a trapezoid method and all that good stuff. So we learned a whole bunch of methods. We learned that, you know, we could get more accurate. We could get more accurate if we wanted the area under the curve by introducing more rectangles. Okay, and it didn't matter if we were using the left Riemann sum, the right Riemann sum, if we were using the midpoint method, trapezoid method, whatever. It didn't matter. We could just add more rectangles. And so we started off with this theory. We said, okay, well, how can we talk about this mathematically? So, you know, mathematically, we introduced sigma notation, right? Mathematically, we used sigma notation to talk about, you know, adding up all of the areas of these rectangles. So we use sigma notation to shorthand adding up all the rectangular areas. Oops, that's not how you spell rectangle. Rectangular areas. Okay, and roughly speaking, it went a little something like this. We said, okay, zoom out so we can still see this picture. So we'll go over here, and we said, okay, we're going to add up a whole bunch of stuff. What are we adding up? Well, we were adding up a whole bunch of tiny rectangles, right? This is kind of where our thought process starts. And let me pause for a sec. In this class, I will take this approach to everything that we do. You will very seldom see me just jump into doing math. I will always ask the question, what are we doing? What is the basic thoughts? And if your goal is to leave this class with an understanding, with a better understanding of what it is that you're doing in this class, I strongly suggest that you do the same. Anyone can learn formulas. Computers can solve all of this stuff for us, but what they can't do is really figure out what is a question asking. And so in this case, the question I'm asking you is to think about, how do we come up with the process of turning this question, which is getting the area under this curve, right, for whatever mathematical thing it'll give us, how do I turn that into math? And we said, okay, well, it just means we're going to add up a tiny number of rectangles. How many of them are we going to need? Well, it kind of depends. How many do you want? And so we say, you know, we started off by saying, okay, well, what if we start with 1 and maybe we go to n number of rectangles, right? We can have however many we want. And so we said, okay, that makes sense. That's fine. How tall is any of those rectangles, right? So, because if we're adding up, the area of these tiny rectangles, maybe I should put that, the area of tiny rectangles. That's just going to be the height of the rectangle times the width of the rectangle. Well, okay, that makes a lot of sense. Okay, so the next natural question is okay, well, we have n number of rectangles. How tall is one of these rectangles? Well, you just, you pick an x value and you figure out what the y value is, right? That was how we did it. We said the height was just, it's whatever the y value is for a particular x value. And just to kind of elaborate what this x sub I is, if we were doing an example, maybe I'll draw it over here. If we were doing a concrete example and we were talking about integrating from, let's say, 1 to 11. So this has a total distance of 10. And if I was doing, let's say, 5 rectangles, and I was using, so let me make that 1, 2, 3, 4, 5 rectangles, okay? Here's my function, right? There's my function, f of x. And I was saying, what are going to be the x values I'm going to pick? Let's say, just for practice, that we're using the midpoint method of approximation, okay? Then, well, I know, for instance, this is going to be 3, this is going to be 5, this is 7, this is 9. How do I know? Because I'm a mathematical genius. And also I like to pick nice numbers, but, they could have been anything if I'd picked nastier numbers. And if I'm using the midpoint method, these x sub i's just mean, what would x sub 1 be? Well, x sub 1 is going to be 2, right? It's going to be this x value right here. It's going to be the first one that we would pick. And then x sub 2 is going to be the next x value that we picked, which in this case would be 4. And so on and so forth. And we stop with x sub 5, which is going to be the last x value that we pick, which is x equals to 10. Okay, so those x sub i's just correspond to the total number of rectangles that we have. It's which x value you're going to use when we're calculating the height of those rectangles. And then the next question is, okay, well, what's the width of all those rectangles? Well, the width is a lot easier to calculate. You just take the total distance, which is b minus a, and you divide it by the number of rectangles. And this right here from Calculus 2 was how we very, roughly started talking about how to come up with an educated guess of adding up all of these rectangles to approximate the area under the curve. Okay, so this was our Calculus 2 approximation. Okay. And also in Calculus 2, we took this concept and we said, okay, that's cool and all, but how do we actually get it to be very accurate? And so to get perfect accuracy, to get the actual answer, do you remember what we do? To get the actual answer, we just took a limit, right? We introduced a limit. We took the limit as n approaches infinity of our little Riemann sum calculation. We said, well, what if we don't just have a few rectangles? What if we just don't have 4 or 10 or 15 or something like that? What if we had, an infinite number of rectangles? What if we increase the number of rectangles? Well, what happens? And it turns out that when we do this, this bit right here, which literally means, add up an infinite number of something, this right here became the integral operator, okay? What did f of x sub I become, right? What did the height of our rectangles become? Well, if we have infinite rectangles, that means we have infinite x values, and so we're not picking for just x sub I, we're not picking just for the first one or the second one or the third one. We have to be able to calculate the height of the rectangles for any x value we want, right? For infinitely many of them. So that becomes f of x. This is still going to be the height of our rectangle. And then what happens to the width? Well, the width of each rectangle up here, the width, we affectionately called it delta x because it was a fixed number, right? So maybe going back to my application up here, what is my delta x? Delta x here is equal to, yeah, it's equal to 2, right? Because that's the width of all of these rectangles. But what happens to delta x as we shrink these rectangles, right? As we increase the number of rectangles and we make them super duper 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 skinny, what happens to that width? Well, the width shrinks and shrinks and shrinks, and it eventually becomes the mathematical quantity dx. It is a small, infinitely small change in the x direction, and that is the width. We pop on some bounds from a to b, and voila, this right here is the actual area under the curve, in 2D, okay? So that's what we did back in Calculus 2. And so now we're going to take this concept, and if you watched the last video, we talked about how, in Calculus 2, we did these things called, we worked with these things called probability density functions, where you could calculate the total probability of something happening based on a particular input variable x. That's what the area under the curve represented. And so the next natural question is okay, well, what if our function is 3D? Okay, what if our function is 3D? It's a function f of x, y, right? So from a tangible standpoint, maybe this is a function that tells you the probability of winning the lottery based on your age and based on your income or something like that. Okay, and so, a natural question would be, is how do you talk about adding up a bunch of values for a 3D function, a bunch of values of a 3D function. Okay, I'm going to abbreviate function fxn. Okay, and so visually, what are we talking about? Well, the idea here is actually very, very, very simple. You might think it's so simple, you're going to start thinking that this class is too easy, and I agree. That is my goal. My goal is to make this class seem like it is, bite-sized child's play for you all. So, in Calculus 3, hopefully we all learned about what a 3D function looks like. I'm just going to sketch a random one, okay? And I will do this for all of my sketches in this class. I know that any 3D function could look like an ellipsoid. It could look like a hyperboloid. It could look like a sphere. It could look like a paraboloid. It could look like something completely nonsensical. Great. I'm just going to draw mine like this just for illustrative purposes. You can sue me later, okay? So the idea here is very, very, very simple. So if you watched the last video, I already talked about this a bit, but what we're going to do is, to talk about adding up values in 3 dimensions. So in 3D, this is kind of an important concept. Our region of integration is now 2-dimensional. It's now 2-dimensional, okay? So you're like, Dylan, what the heck do you mean? Well, if we go back up here, all the way up here, here it is. When we integrated a 2D function, we were actually integrating over a 1-dimensional region, right? Because x just goes from A to B. This is a 1-dimensional region of integration, right? So this is basically asking, what is the total probability that you win the lottery based on how old you are, right? There's only one input variable, one region of integration, and it is 1-dimensional. But when you talk about 3D functions, right, this is a 3D function because we have 2 inputs, right? We have 2 inputs, x and y, these are the inputs. and one output. That's the f, right? Or if you like, that's your z value. This is your output. Okay, so that makes this a 3D value, 3D function. And so it very, very similarly translates from 2D functions to 3D functions, that when we talk about doing integration in 3D, that these regions, kind of very naturally translate to talking about that maybe we have some bounds in the x direction from A to B, but we also now have bounds in the y direction, say from C to D. Okay, and again, maybe my x here represents, maybe this represents your age, and maybe my y value here represents your income. Okay, and so f basically calculates the probability that you win the lottery based on your age and your income. And so if I want to ask you the question, what is the total probability? What is the total probability that you win the lottery if your age goes from A to B, and we'll say your income goes from C to D. Okay, so now we are taking into account two things. Right, so that's the question. How do we go about doing this? And so in 2D, we used to just have 1D region of integration. Now we are working with 3D functions. We have 2D regions of integration. And so what this looks like is, you can imagine that we will just kind of create these little crosshairs here, because this region here in green represents x going between, A to B. But we don't want all of that. We only want the part that is also encompasses the fact that y goes from C to D, right? So our actual region of integration here is going to be just this space right here. It's this 2D little rectangle here. It's pretty simple, okay? And so you can imagine, if we were to talk about doing integrals, we're not there yet, but if we were to think about doing this, in 2D, integrals, or answering a question like this, gave us area under a curve, gave us area under the curve. Okay, in 3D, guess what the integral is going to give us? Okay, the integrals give us volume under a surface. Okay, under a surface. Basically our function, f of x, y. Okay, and so, what does this look like? Well, just like in Calc 2, there's going to be limits and stuff, but the goal of this video is not to cover that. That will be in the next video. The goal of this video is to just talk about how you might approach doing this using Riemann sums. And the Riemann sums operates in a very similar way, right? If I wanted to calculate the volume of this object, right? So the volume, right, of this object. So let's see if I can kind of draw here. Okay, I want this volume here. Okay, that's what I'm trying to calculate. That represents my total probability of whatever the heck it is that I care about. So let's see if I can create a good sketch for you guys. I'll highlight this in a little bit. Okay, so this volume right here, this shape is going to represent the total probability that I win the lottery based on my age and my income. Cool. Now, we have an idea this is going to go to become integrals, and we're going to use integrals. But for now, we can think about it whereas, maybe I didn't know that. And I just started off with the idea that, all right, well, with Riemann sums back in 2D, we took like a point, we took an input point, and we said, okay, well, let's just create a 3D shape. Let's just create a 3D shape here that kind of approximates that volume. Okay, this red thing that I just drew here. Okay, and hopefully you can see that it's not a good guess. But the idea is very similar to calculus 2. The idea is that we are going to add up a bunch of kind of tiny little rectangular volumes. Okay. Now with one, right, there's not much to do. We would just say, okay, well, what is the volume of this shape? And we might say, okay, well, volume, that's easy. That's like length times width times height. Easy peasy lemon squeezy, right? So, okay, no problem. So let's see. What is the length of this thing? And we say, okay, well, the length, let's take that to be in the x direction. So in the x direction, that would be b minus a. Okay, easy. Boom. That's this. That's the length. How about the width? Okay, let's say the width is in the y direction. Okay, that's just going to be d minus c. Okay, that's this. That's the width. Ta-da. Okay, well, what's the height going to be? Well, again, this is kind of the important part. The height kind of depends on what method you're using. If I were using, if it's specified in a problem to use the bottom left endpoint, like this one, then that right there would be my x and y input. So my height would be the z value at whatever x, y input I was at. Now, if I was using, say, the midpoint method in 3D translates to just picking the point that is right in between here, okay? And so, again, hopefully we notice that if we just use one rectangle, it's not going to give us the best answer, and so you may naturally say, okay, well, how could we modify this to make it better? It's not, again, not rocket science. All we're going to do is I'm going to kind of erase this rectangle that I have. And as you might imagine, if I cut this up into more rectangles, right? Maybe I cut up 2 in the y direction and 4 in the x direction. I could create a whole bunch of smaller rectangles that if I were to draw these, and it's going to get pretty hectic in my drawing here pretty quickly, but I will try. That if I were to, appropriately do this for all of them, and this already looks really terrible to draw, but hopefully, we can get that the idea is that more rectangles are better. Rectangular prisms are better. Okay. So, and that's going to give us a better idea of the solution that we're going to try and get. So let's see if I can work an example for you guys really quick. Let's just do a quick one. So, for example, an example. Okay, so let's think of one. So let's say, let f of xy equal the function sine of x cosine of y, and let the region of integration be this. So I'm going to say x is going to go, let's pick some nice values. Let's just do 0 to pi over 2. And we're going to let y also go from 0 to pi over 2. Okay? And so I'm going to try and, actually, I guess I should finish writing the question. Estimate estimate the volume under the curve using 4 rectangles and their midpoints. Okay, so this is what one of these questions might look like. So let's see. Let's try and come up with a drawing for this. So I always suggest, this is also very important with any question. In this class, you will succeed A+ without any effort at all if you can draw a picture. It will help you so much. And that's all I'm going to do. It doesn't even have to be a beautiful picture. Look at mine. I'm terrible, right? We just have to kind of try and get a semblance of an idea of what on earth we are being asked to do. So here is my attempt to do so. This is Y. This is the x-axis. My region of integration is going to be this little 2-dimensional square, I guess, here. I'm going to ask me for 4 rectangles, so I'm going to cut this just visibly into 4 pieces. Yeah, we can do better than that. Let's try this. 4 pieces like so. And my function, what does sine of x, cosine of y look like? I don't really care. I'm just going to roughly sketch it like so, okay? And so what are we being asked to do? We are being asked to use Riemann sums and estimate the volume under this curve, just like we used to do area under curve. We're doing the volume underneath this curved surface, this function f of x, y, and we're asked to do it for the midpoints of each of these, okay? Now, I'm not going to do it for all of them, but I'm going to go ahead and do it for just one of them, all right? So let's take this first one right here. So what does this mean? This means I'm going to draw a rectangular prism that is based, that's height, right, is based off of whatever my z value is going to be at this point. So first and foremost, let's figure out what is this point. Well, this point right here is going to be pi over 8, comma, pi over 8. Now you might be wondering, Dylan, how did you get that? Well, I know if I cut this into 4 rectangles, that makes this pi over 4. And halfway between that, since I'm using the midpoint, would be pi over 8, and same thing in the y direction. And so very, very roughly, my sketch of this rectangular prism that I'm building, that's height is based on, the height is based exactly on the z value that is located at the center of this little square, the center of this piece. That's my rough visual aid, okay? And I'm going to call that area 1, okay? Oh, excuse me, not area 1. We are no longer in 2D, we are in 3D. This is volume 1. Okay? And so the question is, what is the volume of that particular rectangular prism? Well, just like before, volume last time I checked is like length times width times height. Okay, I know this is really going to push your buttons, but what is the length? Let's say this is the length. Right? Let's say that's length. What is the length of this rectangular prism? Well, I hope that we can see that it is simply a distance of pi over 4. Very good. Okay. Now, what is the width? Oops, let's pick a different color here. What is the width of this rectangular prism? Okay, what is the width? Well, again, it is simply just pi over 4. Why is it just pi over 4? Because we are working with nice numbers and hooray. But, calculating it, very similar to Calculus 2. If you need practice with that, just go back to the Lesson 0 video. Okay, and now the question is, what is the height? Well, the height is simply just going to be the value of my function, the z value, but based on that midpoint, pi over 8, like so, okay? And you might be wondering, well, how do I do that? Well, my function was given to us sine of x, cosine of y. So this is actually just going to equal sine of pi over 8 times cosine of pi over 8. Wonderful. And this right here, this is the volume of my first rectangular prism. This is my first Riemann sum, okay? How many more times do I have to do this? I have to do this 4 times, right? I've got to do this 4 times in total until we get the 4th volume based on, you can go in whichever order you want. It doesn't really matter because you're just adding up a whole bunch of numbers, okay? Now, a question you might have as a student, you're like, well, do I have to evaluate this? And the answer is it kind of depends on the question. So for me, if these are easy trig values, okay, so I'm talking, so if these are pi over 4, pi over 3, pi over 2, any of the easy trig values, you need to know these. You need to know these by heart. Okay, at this point, you should know them. And if you don't, this class is going to be great for you to practice. Don't slack off with them. Take an opportunity to practice. Pi over 8, however, it's not easy. And so for this, I would say you can use a calculator. Use a calculator and just kind of round your decimals. Round your decimals. All right. But I would say if you're trying to turn in an assignment, you should definitely show the work up to here, and then you can indicate, and then I used a calculator afterwards. All right. But if this is an exact form solution, so for instance, maybe we were plugging in pi over 4, and we know sine of pi over 4 is root 2 over 2, and cosine of pi over 4 is root 2 over 2. I would like you to leave your answers in exact form. Leave answers in exact form when possible. Okay, it makes it easier for me to grade and also prevents rounding errors on your part. Okay, so this is pretty much it for the first video. This is kind of an introduction to this idea that we can approximate the volume underneath a 3D curve using Riemann sums yet again. But now instead of having one summation, technically, I guess I didn't show this, but technically we actually have 2 sums here, right? We need one that tells us to go from our first rectangle and go over to the second rectangle in the x direction. And then we need another one that tells us to go from the first rectangle to the second rectangle in the y direction. And then the rest of this is pretty much the same. We're just going to have height, length, width, and we can figure out what these are very quickly depending on what the problem is asking us to do. This right here it's very technical. I'd say this is technical definitions. And it's worked out more in the textbook if you would like to kind of see how they use it a little more. But because we're going to not really focus on this is not a numerical methods class. We're going to actually be doing integrals. I'm not going to have you guys focus too much on this, but there are, some of your homework is going to be based on doing something like this, maybe solving one of these problems or a couple of these problems, just to make sure we have the idea. But as you can imagine, Riemann sums will eventually lead us to integrals and integrals in 3D, and that is what the next lesson is going to cover. So I will see you then.